Welcome back. I've decided to make a separate video on Big O for linear search. I've actually already covered this content, but I realized some people were skipping through videos and not watching everything. So if I have a video titled Linear Search Big O, I found more people will actually watch that because it's really important stuff. Same thing for binary search after this. All right, so here's a quick video on how linear search performs, at least as far as time complexity is concerned. So best case, we have an array of 1,000,000 integers or 50 integers. The very best case is that we find the thing we're looking for right away. So that's the best possible scenario, right? But that's pretty rare, depending on the size of your data. The worst case is O of n. So if we have 1,000,000 integers in an array and we're searching for the last one, or we're searching for something that's not in there, we're going to have to look 1,000,000 times. If we have 50 things in there, and it's the very last element that we're looking for, we're going to have to look 50 times. And average is also O of n. And you might think, well, isn't it actually less than O of n on average? Because sometimes we'll find it, right away. Sometimes we'll find it in the middle of the array, 2/3 of the way, 3/4 of the way. Shouldn't that average out somewhere? And the answer is no, not as far as Big O is concerned. We care about just the general trend. So as n grows, as the length of the array grows, or the length of the string, whatever we're working with, so does the average amount of time it takes. Remember, we throw away all constants. So 2n, half n, 0.25n, those are constants. We ignore those and we just simplify it to O of n. Okay, so that's linear search. It's the best we can do with an unsorted piece of data. But next, we're going to talk about binary search, which is much better. And I'll have a separate video afterwards, once we learn how to implement it, on the big O of binary search and how we derive it. That's coming up.